So you can see what I have in my hand right here is an infrared camera. And what we're looking at is an uninsulated wall, which you commonly find in existing houses. And you can see how much that's glowing yellow and orange with the heat that's flowing through it. Now, if we back up and pull ourselves over, now we just have the steady, even temperatures of well-insulated, thermally broken, airtight wall. I'm standing in front of one of our projects here, and what you can see behind me is just a very common American house. It's a mid-century ranch that we're all familiar with, and these are all over our communities. As we start to look at ways as a company that we can help address climate change, resource use, and comfort and health and durability in the housing stock, we had the clear realization that we're never going to be able to build our way out of this. There's no way that any number of new houses we build are ever going to match the number of houses that are already built, and that if we want to have an impact in these areas, that we have to look at retrofitting existing housing stock. So when we're approaching a new construction project, we've got the liberty to design whatever is the right fit from day one. But in a retrofit situation like this, we have to work with what's here. So what we do is we really try and look at the assemblies that already exist and figure out ways that we can work with them easily to get things like continuous air barriers. Or we're looking at existing walls and finding ways that we can integrate continuous insulation into them with minimal effort. All of these things that we know are going to result in a house that's more comfortable and more healthy and more durable and all those things that we're after. So we're downstairs in the basement of the project right now, and basements play by different rules. When we go below grade with a building, now we're having to deal with soil moisture. That soil moisture is always trying to move from more to less, and more is always going to be the soil, and less is always going to be inside the house. So that moisture is trying to move in the form of vapor through to the inside of the building. We want to control that. We want to limit that. We also have moisture inside of the building, which can see the cold surfaces of the concrete as it's inside of the building, and can result in condensation. That condensation can then drip into liquid water. That liquid water can then feed mold and biological growth inside of your wall assemblies and your floor assemblies. So a common principle for us is always trying to work continuous insulation somewhere into our assemblies. So the way we do this below grade, and a way that does it effectively, is that we come in and we space our wall framing 2 inches off of that concrete wall or block wall that we're dealing with below grade. And then this is where we deploy closed cell spray foam in a controlled way because it does the things that we need in that situation. So that 2-inch space behind the frame wall gets fully covered with that closed cell insulation, meaning that we have continuous insulation in the assembly. It's acting as a vapor barrier at 2 inches of thickness from moisture trying to drive from outside to inside. It is also keeping that surface warm, and we don't have a condensation risk, and we don't have that moisture accumulating and dripping through our wall assemblies, resulting in that musty basement smell that most people are familiar with. So it's about choosing the right materials for the right applications for what we're trying to control. For the walls, right behind me, this is the timber fill. The next material we chose down here is timber bat. We have the timber bat in the rims, and then we use the timber bat also for cutting around odd areas where we can't staple, right? We can't staple to this cast iron exit right here, so we have to find some way to fill the rest of this cavity, and we prefer to not do it with closed cell foam, right? We try and use that only in strategic areas where it's needed. So the timber bat allows us to kind of cut and mold pieces that fit in here so that we've got really good cavity filling continuity of a low carbon, high performance insulation material. Behind me, you can see an old masonry chimney. What I want to point out though is this black coating that's down here on the base of the wall. It's on the wall, but we need to understand it as we talk about our floor. And what that coating is that's a coating made for the commercial flooring industry, and it's a moisture mitigation coating, and it's designed to be rolled on or sprayed on or troweled on. What I've figured out over the years is that we can use this material to address slabs, because when we come into an existing house like this, we don't know if there's any type of vapor barrier underneath that slab, and we have to assume there's not. Because when we build a new house now, before we put down the concrete for your floor, we put in a continuous sheet of plastic that stops that moisture from rising up, as well as sealing against soil gases like radon coming into the space. And we don't know if that's ever been installed here, and it's expensive and difficult for us to figure it out because we'd have to cut through concrete. So the easiest thing for us is just to imagine that it's not there, and then we address it topically with that moisture mitigation coating. So the floor that I'm standing on right now, we had the head height in this basement to do this, and you don't always have that option. But in our case, we came in, cleaned the floor really well, and then we applied that moisture mitigation coating on top of the floor. At the same time, we detail around the slab edge to wall connections and anywhere that there's anything penetrating through that concrete slab so that we know that it's treated really well as an air barrier. At that point, we then frame a floor system on top of it. This is just a sleepered floor system made out of 2x material. That 2x is not even pressure treated because it doesn't need to be, because we've got that vapor barrier in place stopping that moisture load. But we take it a step further and we actually apply a zip tape to the bottom side of those sleepers. So if for some reason in the future of this house, in the next 50, 80, 100 years that exists, there's some moisture in there, then that sleeper system is protected, right? We're forming a capillary break in between that framing material and that concrete, acting as a long-term protection mechanism. Then we fill this floor system full of the timber bat, cut it and fit it in continuously so that there's no voids or any gaps in it. And then we go over top of it with our Advantex subfloor in this case. When we look at walls and vertical portions of our assemblies, we kind of want to have them so that they're a continuous R value, right? We want to have anything that is above grade all at the same R value. And a classic spot where that doesn't happen is a rim joist. And what a rim joist is, part of the building that makes up your floor system's interaction with outside. So the first thing for us is we want to figure out where our air barrier is in that assembly. And it's a tricky one to define when the building's already in place. It's an area that has all of those joints coming together and a lot of leakage pathways that come through it, and they're not always easy to reach. So what we've found over the years that is super effective is aero barrier. So what aero barrier is it's an aerosolized product that we put into the house. It's completely non-toxic, and we mist it into the house while we pressurize the building. And what that does is it forces all of that little sealant that's floating through the air to follow the air streams as they're leaking out of the house and collect. That collection starts to build and build and build until it all sticks together, and now you don't have a hole anymore. It's perfectly sealed. Getting these areas well caulked or taped or can foamed in the past is something that would take a ton of time, and it wasn't always super effective. So this deployment of aero barrier allows us to get a really good air seal into that difficult area. The next thing we're going to do is we're going to choose the appropriate insulation to fill up that cavity. I want to have the same R value in the rim joist. They're seeing the same outdoor conditions and indoor conditions, so there's no reason they should be different. We want to match, at a minimum, the insulation that the rest of the wall above it has. There's a couple of different ways we can do that. We can take the timber bat and we can cut it to fit. It cuts really cleanly and it friction fits into those areas and holds really nice full fill in those cavities. Or we might, in a situation like the one behind me, which is waiting to be done, come in net like we do on the walls. And then we're going to dense pack that full of the timber fill material so that we really completely fill that cavity with a good level of insulation. So now that we've discussed all of these below grade approaches that we have, we're going to step upstairs and we're going to look at some of the different zones and conditions that we have there, because the rules are different and we've got strategies to deal with them. All right, so we're upstairs now and I've got my friend Jason with me from Timber HP, and what we're going to walk through is kind of some of the decision making that we use to choose assemblies for our above grade walls. Why don't we talk a little bit about what this material is here? So I'll take a little bit out of the wall here. So this is the fibers shredded up, right? You guys take wood chips, and these are post-forestry wood chips?
Yeah, they're forest product residuals. So it could be from a mill that's making pine boards, or it could be a mill that's making lumber. The state of Maine, as well as many other places across the northern border into Canada and to the south, are experiencing is a decline of an outsource for those residuals. So the green chips that we're buying used to go to paper mills.
So what you can see behind me is what we've developed as an approach over the years for creating continuous insulation or a continuous thermal break in our assemblies. And it's not truly continuous, but let me walk you through what it is so that you understand. So behind this wall that you can see here, we have regular 2x4 framing, 16-inch on center with wood board sheathing. Okay. What we then did is we took 2x3s and we fastened them every 16 inches. That means we only have 1.5 inches by 1.5 inches area where those two things are in contact with one another. Now what the math says is that's a 96.2% reduction in thermal bridging with this approach, which is pretty darn good. Now that we've got this lattice work of our wall here, we need something that's going to fill that, right? Because we don't want to cut little pieces in and around it. So this is where timber fill comes in for us as a great option. So we've got our netting on our wall here that we then do this saddle stapling with, and what that does is put some tension onto the facer so that we don't get bulging. And we come in here and we dense pack with the timber fill material to fill this cavity continuously. Behind me, you can actually see an example of this is where we do density checking. So we come in and we take a core sample and we measure so that we can understand that this is being installed to the level of density that we need.
You know, speaking to that density in particular, that's where we get the thermal values that we are posting at 3.8 per inch, but it also means that the material is self-supporting. There were instances over the years with traditional cellulose where settling occurred and then people think, well, that's junk insulation. You know, fiberglass bats will settle if they're not stapled in place.
So can you tell us a little bit about how wood fiber kind of naturally manages moisture?
Sure. I mean, typically in a wall cavity, you're not going to see, hopefully, a lot of moisture, but we do get air transported moisture that happens all the time when you're not paying attention to that level of detail of air control.
Or the building's going to age over time, and eventually something's going to break down and we're going to get moisture in it over the long term, and we're trying to plan for that long term. So.
Yeah. When we change things, we remodel over time, we add new outlets, there's airflow that moves through the house. And when that moisture gets into an area where it could become warm, moist air to cooler air, there's a potential for it to wet out. If that happens in a cavity that's dense packed with timber fill or has been friction fit with timber bat, this is an area where sort of the wood memory takes over. And we're adding borate salts, first of all, for fire retardancy, but also for...
And those are very environmentally and human health benign material that is in many products that we commonly use.
Yeah, boric acid's used in eye drops, saline eye drops, and eye wash, actually. So dilute, it's not a problem. In any concentration, anything can be toxic to you. But these are naturally mined minerals and salts. Then they're added and they add fire retardancy, but they also help with any kind of biological decay, mold, mildew, all that sort of thing.
As a preventative.
Absolutely.
And that's not just for the insulation, right? We also see that benefit with the other surfaces that the borates are in contact with, right?
Yeah, it's really kind of fascinating that, you know, we are building with wood. We're building with a little denser wood. It's natural that we insulate with wood, but the insulation can actually help protect the framing itself. It's a big moisture buffer too. It can take on a lot of humidity and help mitigate some of that as well.
So more comfortable, even interior humidity condition.
Yes. Yeah.
So we need to address insulation continuously, like we've talked about, in appropriate R values. And one of the places that gets difficult is the corner where your ceiling meets the roof line at the wall, right? And the reason for that is we end up having these thin little spaces here, right? So we chose to thicken this up, right? We intentionally made this trade ceiling detail here, which gave us a little bit more head height in this space and also got us more insulation out here.
It's interesting with remodeling, you're kind of taking what comes with the territory, right? You know, you find all sorts of surprises along the way, of course. But, you know, when we constructed a house like this, and I don't know how old this is, but 70s, 80s, the energy concerns were different. We started paying attention at that point, but there were decades of underbuilding. I'm assuming here you don't have a raised heel, you didn't have that space, and so you can kind of derate your insulation as you get out to the plate, but that's where a lot of problems come in play.
So you have your flat ceiling and then you have your roof coming down and you end up with this little pinch area right there where we're supposed to have 12 or 14 or 16 inches of insulation, we got 4 or 5 or 6 inches worth of insulation, right? And it's also at a spot where we have all those thermal bridges are all coming together, and it's in that little area, this little zone up here, that we lose a tremendous amount of the energy from the building, right?
Yeah.
It's also a condensation risk. Something we didn't talk about here in this assembly is the reason that we have drywall on the ceiling above us and we don't have it on the walls is the drywall in this situation is our air barrier. So what we did is we put in place our strapping here in the walls. We came in and we drywalled our ceiling and we ran the aero barrier to create this and the walls with no insulation as our air barrier. So you've got that continuity down and around the building, right? Just like we want continuous insulation, we want a continuous air barrier around the building. So in this assembly up here, we use the timber fill material in order to get blown into that whole cavity.
And that's really nice use for a blown fiber product, is that when you have these larger, big volume spaces that are not a traditional bat size or frame size, or a lot of complexity in that framing, you can just dense pack large areas.
Just fill them up.
Just keep filling it, and now you've got a wonderful blanket of insulation. It's not going anywhere.
And we're really happy to be pushing retrofits, right? I think this is an area that the industry sees a lot of need right now.
I think retrofits are huge and they're hard. You know, you really, I think, have done a great job pulling all these pieces together. We think of houses as this one thing, but it's really a sum of its parts, and how those parts come together are really critical because they can go south pretty quickly. And I think you've done a wonderful job bringing it all together, address building science along the way, which is really important.
So I appreciate that, Jason. I've won these little tips and techniques and assemblies the hard way over the years, and I'm happy to share them, and I hope that people will take them and try to deploy them on their projects. And I hope that I'll also get some feedback on things that we can do better, because we're always trying to push that bar forward, and we're happy to have partners like Timber HP in this fight.
Glad to be here.